Okay, it looks like everybody's back. Yeah. Okay, so welcome back. I'm very happy to introduce Nicholas Garcia Trilos, who's our last speaker for the afternoon. He's from the University of Wisconsin-Madison, and he's going to talk to us about Wasserstein gradient flows and the search of neural network architectures.
Thank you, Jeff, and thank you all the organizers and the IMA for this beautiful bottle that I'm going to be using, hopefully, as I speak. So today I'm going to talk about a project that I started with Javier Morales, I think a couple of years ago, 2 years ago, and with his brother, Felix Morales, who is an undergrad student and who nonetheless had like this amazing drive to code things and make many of the things that I'm going to discuss today work computationally. So this has been an interesting project from a theoretical perspective, but also from a computational perspective. And so, of course, like in line with the theme of this workshop, I will talk about theory and algorithms that are related to graphs. But the graphs that I will be thinking about are not graphs on data, and I'll explain in a moment what these graphs are and essentially where the theory comes from that motivates the algorithms and ultimately what are the algorithms. Just a little comment on this work is basically based on these two papers that are from this summer. The first one is theoretical. The second one is the more applied one. Thank you, to my sponsors and especially to the CS CAM at the University of Maryland, who basically they borrowed the computational resources that we needed to run everything. All right, so let's just, a little outline of the talk. So I'm going to introduce what is the neural architecture search problem. And then with that, I will, I basically will for a moment switch topic for a little bit, and I'll talk about semi-discrete optimal transport and somehow some of the geometric structure that comes with this problem or this this structure. And of course, like the idea will be to relate back to the neural architecture search problem. All right, so what is the NAS problem? So let's take a data set like the SciFar10 data set. So we have a bunch of images from different objects, including animals. And, so then we have some data that, basically the data are images. These are labeled into one of 10 classes, basically. And the idea is, when you use a neural network is to, try to build this very sophisticated infrastructure to try to basically match inputs with outputs by optimizing over some parameter space. And then, of course, what you're trying to optimize is some loss function. I guess for notation, really, what we have here is that once you give me a neural network with architecture G, and once you give me the parameters of that neural network X, then essentially what I'm creating is it's a map between inputs and outputs. Okay, and so of course, like that cartoon picture that I had there, it's a little bit more sophisticated. So there is a composition of units that basically map you from inputs into outputs. Okay, so here I have an example of an architecture, a neural network architecture. And this neural network architecture is used to classify the SciFar10 data set. Okay, so the input is in this node over here. And, there is all these transformations that happen. And of course, at the end, there is like an output layer. Now, this is an image where, although it looks kind of like nice and simple, inside each of these units, there are many things happening. And just this network has something like around 20 million parameters that you're trying to optimize, okay? Now, of course, okay, so just what is the training? The training is, well, you have some loss function V, and for the given architecture G, you're trying to find the best parameters for this architecture. Okay, so this means training the network once you're given the architecture G. Now, of course, then the question is, well, but this architecture seems kind of like a little bit ad hoc. So how was this built? Was it, constructed by humans, or was it designed by something? And well, essentially the neural architecture search literature and methodologies essentially are about finding those architectures for you. Okay, so it's not about asking someone to design something that has millions of parameters, but rather iteratively in a data-driven way, try to come up with good architectures. Okay, so really, in a very simple description, the problem of neural architecture search is kind of like an optimization over two variables. One is the architecture G and the corresponding parameters X, and V here is still a loss function that you define in terms of your observed data. Okay, so that's in short what the NAS problem is. And in the literature, there are at least three big kind of approaches to address this problem. Okay, so perhaps one of the biggest ones is the reinforcement learning approach, and I'll make some comments about this. There are also approaches for solving this problem that are based on evolutionary algorithms. And there is the hill climbing strategies, which is the framework that I will be using later for the rest of my talk. Okay, so just to give you a sense of what this, for example, the reinforcement learning approaches are about. So there is this paper by Sov and Lee. So they work at Google Brain. This is a paper that has received thousands of citations. As you can imagine, this is a very hot topic. Anyway, so just to get like a very basic description of what's happening here, there is a notion of a controller that basically is trying to learn how to sample architectures. And basically the controller proposes an architecture. This architecture gets trained, and then depending on the kind of outcome in terms of score or loss that this architecture gets, once it gets trained, then it basically sends information back to the controller, and the controller adapts its likelihood to produce new architectures, and the process continues like this. Okay, so of course, one thing that it's important to notice here is that there is clearly like a bottleneck in terms of computation, which is that every time that an architecture gets proposed, at least in this basic formulation that I'm describing here, you have to train this full network. And if we're talking about networks that get increasingly more and more complex, then of course, training one of those networks is going to take longer and longer. Okay, so there are some approaches that people have considered. So instead of trying to evaluate exactly kind of like the quality of a network once it gets fully trained, then there are like surrogates for the score fully trained, and so as to alleviate a little bit the computational burden of fully training a network. Okay, but essentially this is the structure that appears in these reinforcement learning approaches. Now the framework that I'll be using later on is this hill climbing strategies. Okay, so this appeared 3 years ago in this paper by Erickson et al. Again, a highly cited paper. And it basically proceeds by repeating kind of like what appears in this figure several times. Okay, so then basically at some point maybe you start with a simple model, and then you apply a notion of network morphism. So that means you have an architecture and you're going to apply some transformations that will create new models, new architectures, and then you will train each of these new models. And then essentially you will train that for a fixed amount of time. Then you will see among your submodels which one perform better. And then from there, you will basically restart the process, basically generate new networks from new architectures from this best performing one, repeat and again. You do this until you have reached a large enough size for your model. You start with a very basic one. This will become more complicated as the process goes on. And then, you put like a stopping criterion where basically you say, okay, for example, if you have more than, I don't know, a certain number of parameters, you stop, or one measurement that people use typically is the number of convolutional layers in your architecture. So that could be a stopping criterion. Okay, so something to emphasize, and this will in a sense is going to motivate everything that's going to come afterwards, is the fact that in this approach, the amount of time that you use to train these models that you generate is fixed. Okay, so this is a parameter that someone specifies, but it's not determined by essentially the internal structure of the learning problem. Okay, so it's not going to be based on the data, but it's just like something that you fix as a parameter. Okay, so in a sense, a lot of what we're going to do later is motivated by this process here. So instead of trying to fix a parameter that you decide on before the learning, this parameter in a sense is going to be automatic and is going to be determined by some dynamics that we will consider later. Okay, so this is key for what follows. Now, so just to give you a few words on this idea of network morphisms. So this idea is as follows. So once you're generating new architectures from a starting one, basically the idea is to create essentially a map that sends you from an architecture with its, say parameters X into a new architecture G tilde with associated parameters X tilde. And the idea is that when you're creating these new networks, the idea is that these maps satisfy the property that at least at the beginning, once you do the transformation, essentially the mapping, the input-output mapping for any input is essentially the same. Okay, so and one can show that essentially you can do a bunch of operations on architectures and choose a transformation of parameters that would satisfy this property. So at least you would know that once you apply these morphisms, you are not losing accuracy. You're essentially at the same value of accuracy once you apply the transformation. Okay, so things that you can do, for example, is to make networks deeper. So you can add convolutional layers or batch norm ReLU layers. You can do all of that. And there is a choice of parameters, X goes to X tilde, that would allow you to respect this property. You can make networks wider, in particular add channels, enlarge fully connected layers, add skip connections. You can do all of these things. So all these operations would enter into this framework of the network morphisms. Okay, so there is a very, very big literature on neural architecture search. This grows, every day. It's a very, very big area. And of course, like in this setting, one of the things that motivated us, Javier and myself, to really start working on this problem from a mathematical perspective is to say, well, is there anything we can do, especially in specific instances of these algorithms, that can help can help these algorithms basically? And so, so in a sense, like what I'm going to discuss now is a framework, a mathematical framework that ultimately will motivate us to introduce certain steps in algorithms that potentially, and in fact, what we experimented showed that it does improve upon existing neural architecture search algorithms. Okay. So, okay, so now I have introduced this problem, and what I'm going to do now is I'm going to talk about math. Okay, so suddenly this is going to become a mathematical talk, but keep in mind that most of this is going to be motivated by the problem that I just introduced. Okay, and we will get back to that at the end of the talk. Okay, so let's just ask this question. So imagine that you have an optimization problem on a semi-discrete space. So for me, semi-discrete space is an Euclidean space cross a finite set. And in this case, this finite set it has a geometry. So it has the geometry of a weighted finite graph. Okay, so the K here, it has to do with the strength of connections between nodes in G. Okay, so at this point, this G is abstract, but of course you start thinking, okay, maybe this is going to be related with architectures. That's indeed the case later on. And here RD, I'm imagining that is the same for everyone. So this is kind of like a very simplified setting where it's kind of like we're working on a tensorized setting where essentially for every node, I have like a fiber, and this fiber is the same for every node. Essentially, it's RD for all of them. The dimension doesn't change. Okay, so this is a simplification, but it will motivate things later on. So now what I want to ask is, are there gradient-based methods for optimizing a function like this? And of course, you would say, well, but you have a discrete structure here, so how can we even talk about a gradient in that setting? Okay. Now, to try to answer how to propose gradient-like descent methods for an optimization of that form, I guess it's it's a good idea to rethink or revisit what we do in Euclidean space when we talk about gradient descent algorithms. Okay, so if we have a minimization of a function, nice function, how can we do optimization? So of course, like the gradient based methods, popular ones are described in these three systems that I'm presenting here. So the first one is gradient descent, typical one. The second one is gradient descent when we add a little bit of noise, helpful perhaps. It can help escape local minima and stuff like this. And then the third one is a particle method where I'm kind of trying to find consensus among different particles that I throw over the space to, just try to explore a little bit more. Okay. So now the observation is that all these three systems, in a sense, are closely linked to gradient flows in a space of probability measures. Okay. So all of them are connected to gradient flows of probability measures. So for example, the first one actually is a particular case of the second one. And then the second one is the Langevin diffusion, which is connected to the Fokker-Planck equation, and that in a paper by Jordan, Kinderler, and Otto, a very seminal work, it was shown that essentially that evolution could be characterized. The evolution of the distribution of this system, a stochastic system, can be characterized as a gradient descent in the space of probability measures, okay, in RD. And then what about this one, this other one, in a recent paper by Garbuno Inigo and collaborators, they also showed that, okay, there is an interpretation of this particle system from the perspective of gradient descent on the space of measures with some metric structure, okay? All right, so now just to work on something concrete, let's just recall a little bit about this result of Jordan, Kinderler, Otto, and basically just to make a little bit more precise what I said earlier. So what I'm saying is that the distribution of this stochastic process solves an equation that looks and can be interpreted as a gradient descent equation. Okay, so here the initial location of this distribution, mu0, evolves according to basically a gradient flow where the energy that you're trying to minimize is a relative entropy energy, and the metric that you're using to define your gradient is the Wasserstein distance. Okay, so I remind you, maybe you've seen this before, maybe not, but the Wasserstein distance is a metric on the space of probability measures that have a square integrable they have finite second moments. It is defined, it has this static formulation where you are trying to minimize the cost of transporting mass from one location into another, and you are penalizing the distance traveled to do that. So this is a static formulation because it doesn't specify how you're transporting the mass continuously in time. You're just saying mass goes from one place to another, and that's it. But it's not telling you how you do that dynamically. Fortunately for us, and you'll see this later on, there is a formulation, a dynamic formulation of the same optimal transport problem, which is, but the name suggests it, it's dynamic. It tells you what is happening continuously in time. Okay, so the idea is that you're basically saying, well, I want to move mass from mu to nu, and what I'm going to do is I'm going to continuously move this map following something, a process that will preserve the mass along the way. And I will try to minimize basically the energy that I have to consume to be able to move the mass from mu to nu, okay? So the idea is that this formulation exhibits some qualitative property of the Wasserstein distance, and is that essentially it can be seen as a Riemannian, as a Riemannian metric on the space of probability measures. Essentially, if you remember what geodesics are in Riemannian geometry, basically what we have here is like we're trying to connect 2 points by a curve, and then we're trying to minimize the length or something related to the length between those 2 points. Okay, and that is the way you would define a geodesic distance. And so this formulation of optimal transport in the Euclidean space makes it explicit that this space has this Riemannian structure. And so when we talk about gradients, then at least at a formal level, we can make sense of equations of this type. Okay, so all right, so that was kind of a motivation from what happens in the Euclidean space. And then of course we're saying, okay, so people do, you know, we can lift our dynamics that are gradient descent in the usual sense, we can lift them to the space of measures and still have an interpretation as a gradient descent equations. And so now that we return to our semi-discrete problem, we can try to think along the same way. So basically, we're going to now interpret our gradient descent equations now in the lifted sense. So for that, of course, what we would need to do is define or introduce an analog of the transport distance, but now on spaces of measures on the product space RD cross G. Okay, so that's the first thing that I need to do. And for that, in fact, the very, very first thing that I need to introduce is the notion of curve in that space. Okay, so how do I move from one measure on my semi-discrete space into another? And of course, like the natural extension to this case would be to consider a semi-discrete continuity equation, where I'm saying that the change in mass at a given location is due to, well, basically mass is being transported either in the x direction, which is what happens in this term, or in the g direction. In other words, I'm trying to exchange mass between different nodes in my graph, okay? In principle, the mechanism in which I'm transporting mass from, along x versus along g could be driven by different functions phi and psi, okay? So at this stage, phi and psi don't have to be the same. In fact, they could be different. Here, there's just one observation. Of course, the divergence term here is the usual divergence from partial differential equations. For the graph, we need to give a definition, and in fact, we need to interpret everything that appears in this formula. Okay, so then this divergence is intuitively the same thing as the divergence on the continuum. So you're just trying to understand how much stuff is flowing from a given location. Okay, so just to define what that divergence would be, it would be here, we would have the gradient in the g coordinate. So because g is discrete, this is just like a finite difference. And then I would need to interpret what do I mean by the mass multiplying this gradient, okay? Because in a graph, a gradient is a function that lives on the edges. And in the Euclidean case, I can multiply scalars by vectors. But when I have a graph, how would I do that? Well, the only possibility would be to say, well, if the mass is only defined on nodes and I need to multiply by something that is undefined on edges, one way to do it is to interpolate the values of the mass at the nodes that correspond to a given edge. So this is the role of this object over here, is interpolating the amount of mass that I'm representing here by ftxg, located at the point x and g. And I'm interpolating the amount of mass with the amount of mass at the point x comma g prime. Okay, so this is a choice that we have to make. How are we going to interpolate the mass? And this will have a consequence. Is basically, for larger values of theta, it will mean that mass can flow easier in a much easier way. If theta is much smaller, then it's like putting some restriction on how much mass can flow on a given edge. There is also this basically KGG prime, which is, it has to do with the geometry of my graph, which in principle I could incorporate into my interpolator, but I guess I prefer to separate it and put it right here. But it's something that we have to choose. Okay, so in fact, not that we have to choose. This comes from the graph that we're playing with. Okay, so that's what I'm highlighting there. All right, so now once we have the notion of a curve in the space of measures on my semi-discrete space, now we can introduce the Wasserstein distance between these two measures in a very similar fashion as what was done in the Benhamou-Brenier formulation. Okay, and also in the same way that it was done in the discrete optimal transport business, which is basically if you omit the first term that has the real or the RD component, essentially that would give you the discrete structure. Okay, so this was so in a sense this definition is motivated by the work of Chow et al., Alexander Mielke, and Jan Maas about 8 years ago or something like this. Okay, so this is going to be our metric. And as you can see, this already, has a kind of explicit Riemannian structure in a similar way as what I described for the Benhamou-Brenier formulation in just RD. Okay, so here are my curves, and here are my, basically like the energy functional that I'm trying to minimize along the curve. All right, so, okay, so now I'm going to make a few comments about what can we do with that Riemannian structure, okay, or just with that definition. Okay, so I'll mention a few things about the Riemannian structure. What can we do to obtain gradient flows? And in fact, what I'll show you is that you can also involve higher order dynamics for optimization of algorithms, okay, for optimization of energies. So, okay, so let's just start with what is the Riemannian structure here. So in fact, what is happening here is that basically to describe infinitesimal changes of measures, the only thing that you need to choose basically is a potential, which will define this, basically it will determine the velocity fields both in the x coordinate and in the g coordinate that you can use to transform the mass infinitesimally, okay? Now, one observation here is that although in principle, I said that these two mechanisms, how you change mass in X and how you change mass in G, they could be different. It turns out that optimally, you would always pick the same potential for both X and G. Okay, so there is only need for one potential. And this has some interesting consequences, and it will allow us to later do analysis on second order dynamics, for example. Okay, so it was important for us to identify that the best choice that you could make was, well, you always would pick the same potential, you wouldn't pick different potentials. So basically what we were doing there was characterizing the tangent plane of our manifold of distributions. And of course, then the analog in the corresponding inner product would have this form where you're basically penalizing the x derivatives of your potential, but also the g derivatives of your potential. Okay, so in a sense, you always have these two parts. One part is continuum, the other part is discrete. All right, so now once we have this kind of tangent plane interpretation, this Riemannian structure, then we can start doing things at least at a formal level, as we would do in the Riemannian geometry setting. Okay, so what that means is that we would say, okay, so if we want to define the gradient of a function on M, what we will do is just look at curves and basically just see how the energy changes along a curve. And whatever appears on the left-hand side, that's going to be my definition of gradient. Okay, so we can do that for an energy like this type, where we have our potential, maybe the energy that we're trying to minimize, and then maybe we add a little bit of noise, so we introduce something like an entropic term. What we would have to do is, using this formalism from Riemannian geometry, do something like this to try to identify who is the potential that goes there. That will be my gradient. And when you choose the entropy to be, entropy on two coordinates, turns out that your gradient will have essentially this form. And when you do that computation for an entropy that only penalizes the marginal on the g coordinate, it will have this form. And so this is just a computation that one can do at a formal level. Okay, so then basically, once you plug in back this potential into the continuity equation, you get this systems of equations that basically are describing the evolution of your mass as time goes by. So one observation here is that this equation here, which is, I mean, from the PDE perspective, is a couple system of reaction diffusion equations. If you're indexing your equations by the nodes of your graph, this first appeared in the work by Alexander Mielke. The only thing is that in his work, he was not characterizing tangent planes, and as you will see, he was therefore not characterizing either the second order dynamics that I will motivate in a moment. Okay, so now let's talk about a little bit about second order dynamics. So again, we go back to differential geometry and we say, how do we define geodesics? How do we define something like Nesterov accelerated dynamics for optimization? So formally, this is the type of thing that you would do. So geodesics are, well, you want the acceleration of your curve to be zero, basically. And here, for accelerated dynamics, what you want is that the velocity for how you're changing your parameters, essentially, is determined by an equation of this form. And if you choose gamma appropriately, this will essentially reduce to Nesterov, at least in the Euclidean case. Okay, so here P dot, the derivative of the velocity, in other words, the acceleration in the differential geometry kind of language would be the covariant derivative of the velocity of the curve, and then you're applying that covariant derivative to the velocity itself. Now, how would we find the analog in the Wasserstein setting? Well, we again use some formal computation. We check our differential geometry book. We realize that this covariant derivative of a curve of the velocity of the curve against itself can be characterized by looking at variations of basically the energy function that would appear in the definition of the distance, basically. So it's something like related to length square. Okay, and so the idea is that you have your curve Q, and you're trying to identify what is this acceleration. Then what you are going to do is find perturbations of this curve. So these perturbations are parameterized by this number S. And then what you're trying to do is basically, from this formula, just taking variations of the energy as you change that little parameter, as you change a little bit your curve. And then by doing that, you're basically going to be recovering your acceleration, okay? So we can do exactly the same thing for the Wasserstein distance. And then basically once you do this computation, so it takes some, a bunch of lines, but ultimately you get to a point where you can characterize what would be the acceleration of your curve. Okay, and so once you plug in those dynamics, that potential into the continuity equation, what you get is the analogs of, well, what are the geodesics of this space? Okay, so they would be characterized by these two equations. The first one is just saying, well, this is the continuity equation, that basically, what is the velocity of your curve? And then the second equation is saying the acceleration is equal to zero. That's basically what that says. The second, the accelerated dynamics, well, basically, the first one is saying, what is the velocity of your curve? How are you moving in this space? And then the second one is telling you how is the acceleration changing in time. It basically matches what you would have for the accelerated dynamics in the differential geometry setting. All right, so here I guess I could do like a very quick, there is another way of introducing gradient flows, which it has to do with maybe less of this Riemannian formalism and a little bit more rigorous in a sense, which is via this minimizing movement scheme. You're trying to, this is like trying to do implicit Euler scheme on this metric space in our space of probability measures on RD cross G. And then, okay, so there are some theoretical results that with Javier we obtain, which basically relate this minimizing movement scheme rigorously for some static optimal transport problem on this semi-discrete space with the equations that we had seen earlier, basically. The same ones that we motivated from a Riemannian perspective appear also here from a different, perhaps a bit more rigorous setting, okay? All right, so I think this is the end of my, this is the end of my side note, and this is the end of my kind of a digression on semi-discrete optimal transport. But what I hope that you get from all these slides is just the last piece, if you like, that these equations here are basically characterizing how you would evolve in the space of measures on the semi-discrete space, and that in a sense this is connected to trying to do some sort of optimization on the basis space, which is what we cared about. Okay, so this would be the gradient descent equations on the lifted space. Okay, and so now of course then the question is, okay, so how are you going to use that for neural architecture search, and what's the implications that has? Okay, so okay, I'm going to give you right away an algorithm. Okay, and this is inspired by those dynamics that I discussed earlier. Okay, so the idea is essentially to try to do the same kind of construction as in this hill climbing strategy, but instead of letting networks get trained for a fixed amount of time, the way that we're going to decide whether we have to, basically reassess which network has been is doing much better is dynamically determined by the dynamics that some dynamics that we're going to impose. So in a sense, you have to think of this algorithm as kind of some sort of discretization of the equations that I was talking about earlier when we talked about this gradient descent on spaces of measures. Okay, so here step one is like in the hill climbing strategy, you have one network. The second step is you're going to apply network morphism. So now you're going to have a little local graph. So now we're going to be moving in a local graph. And then we're going to run some particle dynamics. And these particle dynamics are going to be mimicking the type of equations that we discussed earlier. Okay, so then we're going to run these dynamics, and I'll explain what those are in a moment. And then after some criterion that has to do with the dynamics and not with the kind of out the loop parameter tau, we're going to stop those dynamics. Okay, in this case, I said, just to be concrete, pick once there is a majority of particles in one location, then we stop. And then that's the way we're going to choose our new architecture, if you like. And then from there, we're going to continue this algorithm of reconstructing by morphisms a new graph, and then selecting the best one, and so on and so forth. Okay, so this was my point when I was describing hill climbing. The main difference in what they do and what we do, because again, what we're doing is building on top of what they do, is we're not going to be using a fixed parameter to make the decision on what is going to be the next best architecture, but rather we're going to decide that based on particle dynamics that are inspired by the gradient flows that I described earlier. Okay, so just kind of to make this a little bit more concrete. So we have, at some point we have an architecture G with its parameters, its current parameters. Then we're going to apply network morphisms. That's going to induce other architectures with parameters that, in a sense, provide the same type of input to output mapping. So that's the property of the morphisms. Then perhaps we can, here we have a choice on how we build a graph. Okay, so I mentioned that the graph is something that is given. So here we have a choice, and maybe later we can discuss about that, like how do you choose the graph. But suppose that you enforce a graph on this nodes of architectures. Okay, and so now we're going to initialize the dynamics, and this is going to be very simple. It's going to be kind of like in a sense, this is kind of like a splitting or coordinate descent, if you like, inspired by the gradient descent. So we're going to be updating the x coordinate. So we're going to be updating parameters. So basically, this will be in the neural network language, it would be training. We're just like for every element in our graph, Essentially, for every element in our graph of architectures, we're going to be updating the corresponding parameters. And then, there's going to be one step like that. And then the next step, there's going to be some mutation. So some particles that I had on my graph are going to start jumping from one architecture to the other. They want to go to other architectures. And in this case, if you remember some of those equations, there's again this kind of a difference between the entropy and the potential that we're trying to minimize, that will determine if particles are going to try to jump from one location to another, and so on and so forth. Okay, and then once we have decided particles are jumping or not, then they will decide to which architecture they're going to jump based on this quotients. Okay, so the idea here is that particles will try to go towards regions that are that have better V, but at the same time, at least for this entropic term that I'm putting here, they're also going to try to explore. Okay, so this idea here, the idea is also to induce some exploration of the space. Okay, maybe just one comment here. So let me explain a little bit again, how is this particle dynamics work. So initially, I'm going to put all my particles here at the center. This was the initial loaded architecture that I have, and then I'm going to run this dynamics. So each of these nodes is going to be updating its parameters. And then the particles are, you can think of them as casino chips or tokens, where essentially I'm just seeing these architectures kind of racing as if they were horses. And then these chips are going to be reassessed as time goes by. So the particles here, for me, my interpretation is more like casino chips. Initially, we're betting everything on the initial architecture, but as we see things evolving, we're going to start reassessing and putting chips on different architectures until one of them is dominating the other ones. And in some sense, I mentioned earlier, as soon as it has twice as the initial one, then we stop, and whoever is winning at that stage or something like that. But again, the time that it takes to reach that conclusion is not something that we specify. And then this is going to have some consequences I'll mention in a moment. All right, so what I was saying is that once we stop the dynamics, there's going to be a new architecture that we're picking. In this case, it's going to be, let's say this one over here. We update our current architecture. We update its parameters. It's the ones that we currently have. And then we start the process again, from that new architecture, we generate new architectures, and we do this again and again until we reach some stopping criterion. If our architecture has reached a certain size, then we stop. Okay, so we did this for the CIFAR data set, and then we use this NASGD algorithm, the one that I described earlier. There is some modifications that I don't have time to explain. But essentially, the picture that I showed you at the beginning, it was the architecture that we obtained using our scheme. There is, of course, the accelerated version of what I mentioned earlier, which is, of course, it involves this momentum variable. And okay, here I'm not going to say exactly how the particle dynamics are for that setting, but my point here is that you can also come up with an analog now using second order dynamics. And then, okay, so this is the picture that we get. They're actually different, although of course they look quite similar in a sense. Okay, and so here just a few comments on results of that we obtained. So here we were comparing our algorithms, the way we were deciding how to decide which one was the best architecture in each of these inner loops, essentially, versus the other hill climbing kind of based approaches, or better than hill climbing, let's say network morphism approaches. And so as I said, the number of parameters at the end of the computation, the final networks are very, very huge. There are tens of millions of parameters in all cases. At least, in the case of the original hill climbing paper, it's in this order. This is here the error of approximation on held out data and on test data, basically. So we do get better error, while essentially, if you see the computational resources in terms of time, at least for the gradient descent, is much lower. So the idea is that we reach much faster, like bigger networks. And essentially, the explanation for this is what I have been emphasizing during my talk, which is that choosing that parameter tau that tells you how long you have to wait until you decide to stop the training of networks. So basically, by dynamically doing that, following dynamics, particle dynamics, or our gradient descent dynamics, basically we were able to see that basically we would test 40 architectures when they were testing one. In other words, we were getting rid of architectures much faster. That process was accelerated. And the point is that it would be kind of difficult to tune that parameter because there is no real kind of there is no principal way of tuning that parameter in their case, but for us, the tuning happens naturally from the dynamics. It's a consequence of the dynamics that we have imposed. Okay, the results for between NASGD and NASA-GD, like the accelerated version, okay, here you get a little bit more better error, but okay, we run this for longer. So at least in terms of comparing those two, it's not very conclusive yet. There is work to do over there. So I think I'm running out of time, so I'm just going to mention just one idea that, in doing this, you need to be careful with, and is the idea of overfitting. Of course, overfitting can be a problem even just from training one neural network. If you imagine that you're on top of that adding a surge of architectures, then overfitting would be a much more prominent problem. So one thing here is that, the V that we use, so the loss function that we use, typically this is on data that we observe data, we have a collection of data points. Well, the idea is that in the two steps of how you are assessing the, the mutation versus the training, the data sets that you use for both parts are completely different, so that you don't contaminate the choice. Basically, it's like in a model selection setting. You don't want to contaminate basically create overfitting in the process. Okay, so this is just a simple idea. There is a lot of avenues to explore. So well, first of all, okay, so what I talked about was this framework based on optimal transport to produce variational inspired NAS algorithms. And okay, we work in the network morphism setting, but again, our perspective is not just to restrict ourselves to that. We restrict it to be concrete and, well, to make the experiments, but we believe that this idea of trying to come up with specific steps in the way in the way people do things, try to modify some of those steps in a principled way. We believe that doing this can have a big impact, and this is somehow like what we were trying to test in this first kind of attempt, let's say. One thing that being able to test more architectures much faster. One thing that we thought was quite interesting, and perhaps for potential kind of research, is what about combining with reinforcement learning approaches? Because of course, reinforcement learning is good when you get more and more data, basically. So the more architectures you try, the better the controller gets, and then in turn, the better the controller is going to predict good architectures to predict. So we see that there is a positive loop here, a positive feedback loop that we can exploit. But of course, this will have to wait for further research. There is a lot of degrees of freedom to investigate. If you were wondering how many morphisms per step are we using, well, keep in mind that for every morphism that you apply, so for every network that emanates from a single one, you're going to be training that network. So that means that you cannot be trying too many of those, because, okay, this will be memory burden and also computational burden. But it's still, like, how would you, how deep would you be exploring the architecture space on every step, let's say? different graph structures. All our experiments actually were very basic. We considered a complete graph. There are some settings where you would imagine that giving different weights may be of interest. So for example, here I talked about network morphisms. These ones tend to make the models bigger, but there may be some reasons to try to go backwards, like to try to make networks smaller. And so one way to, of course, like in terms of loss functions, the complex models would be stronger, but then by adjusting the weights in your graph, you could give some kind of possibilities or probabilities to go backwards. And so in that way, you can motivate exploring the architecture space backward and forward. Different dynamics, this is very basic what we did. I think that there's so many ways to come up with particle methods, so many equations that you could explore, entropy versus fast diffusion, or actually even better, slow diffusion. These are all questions that remain. Different frameworks, accelerated dynamics, yes or no. It's not, at least our experiments were not conclusive on that regard. And then of course, from the theoretical level, just putting aside the neural architecture search, there is this, I think interesting problems related to better exploring this static and dynamic formulations of semi-discrete optimal transport, exploring Finslerian structures, convergence of particle methods, etc., etc. This is ongoing work, but I hope that I have, at least give you a taste that there is a lot of interesting applications that are closely related to what computer scientists are doing right now, and that involve serious mathematics and that are waiting to be addressed, I guess. So with that, I thank you for your attention.
Okay, thanks for the really interesting talk. If there are any questions from the audience, please type them in the chat box or raise your hand. And I'll start off asking a couple of questions. This seems really interesting. I was wondering you were saying it's a lot of computational burden because each morphism you have to retrain the network. Do you start from scratch with like weights being random, or do you sort of initialize from the ones you already had?
So that's the nice kind of idea in that network morphism paper, and that was this kind of this property of, once you initialize the parameters of the new architecture, you guarantee that you have this property. In other words, that the loss function is at the same level from the starting network G and the network G tilde. So in other words, here this X tilde is already initialized for you, guaranteeing this property.
I see.
And it's actually a simple observation. It's, for example, imagine that you want to split, if you want to create a new channel. So then basically creating a new channel later on, they're going to have to be together. So essentially you're splitting and you have to involve two matrices, and one matrix, for example, is initialized as 0. So you just kill that part. But in that simple way, you guarantee that those parameters initialized in that way are behaving like the previous network. So in that sense, this was an important kind of a contribution in this network morphism, precisely for what you're saying, that you don't have to train from scratch the networks that you are kind of proposing. That contrasts a lot with for example, the reinforcement learning approaches, where at least the original ones would immediately, as the controller proposes one thing, and there is no connection whatsoever between the one that the controller proposed earlier and the one that is proposing now. So there is no way to initialize in a smart way the new network. So this was nice about this framework, that we thought it was.
Okay,
Can I ask?
Yeah, go ahead.
Yeah, okay, so I wanted to just ask, well, I guess clarify. So, okay, so G is your neural network, and then X is the parameters for the neural network. So I think you made this assumption that X is always in the same space. So does this mean you have the same number of neurons in each neural network?
That was for the motivation. Okay, so for the motivation, I wanted to have the same RD for all of it, just to talk about the equations. But maybe, and of course, that was a little bit rushed at the end. But I can show you in the dynamics that we consider. So you see, so the thing is that the way that we're interpreting this is that, so okay, maybe in this picture is better. So it's not that every particle will have its own parameters. Okay, so because if we were allowing to do that, then we would be training as many architectures as particles, and of course this would be too limiting. So if n is if the number of particles to decide on this, on what is going to be the next best architecture, if the number of I mean if the, what was I going to say? Yes, so if each of those particles had a like a free parameter, then this would be computationally very prohibiting. So the interpretation here is that each of these nodes, which is each of the possible architectures, is training something. Okay, so in a sense, there is no interference between the parameters here and here in the dynamics that we're considering. The particles are only used to decide, in a sense, which one is better. So here, what we're saying is, like, suppose you have a particle I located at one of those nodes, and you just want to decide whether you're going to move that particle to a new coordinate, a new architecture. So it's going to go from one node into another. So that is determined by the parameters that the node where that particle is at. So this xg that I wrote here, and then this xg tilde is the parameters of the other nodes of the other nodes. So it is in that way. So yes, I agree that this is like a small modification of what initially the gradient flow dynamics would suggest, but this is somehow almost necessary if we want to maintain kind of the computational burden control. One can in principle allow this x to also depend on the particle, but then again, so in other words, these particles would truly be particles on G cross and whatever space you have for that particle. But then in that case, well, again, particles may end up with different parameters, and therefore what that would mean is that you would be training many different networks. So that's why we didn't do that.
Okay, I guess another question is, so you need like, I guess, how did you build your graph of neural network architectures? I guess you need two things. I mean, first of all, you need a lot of candidates of the neural network architectures. And then the second thing is you need to have weights between the neural network architectures.
So the way you select or like you get candidates for nodes is you just do basically you just randomly sample one of these network morphisms. So for that, you have like three types. I mean, again, so making it deeper, making it wider, or adding skip connections, at least in this framework. And then once you have decided which one you're going to do, then you have to decide where you're going to make that, where you're going to make it deeper, like where you're going to make a space, or what you're going to attach, where you're going to attach the new channel, or where you're going to do the skip. So all of that is done randomly, like uniformly. And it's not that terrible because, I mean, at the end of the day, I mean, just think about, let's look at so here, this is kind of more or less the number of units that you have. So even if each of these individual units is like massive, for example, you see here, there is a skip connection. So if we had decided to do a skip connection, we would have, and say that we had decided to do it at this guy. Well, there were not too many options. There are like, I don't know, 18 or something like that option. So it's not that bad, like that part of sampling where you're going to do. But in any case, the short answer is randomly, those are determined. So that's for the nodes. And for the weights, this is the part that I was saying that is like a free parameter as of right now. So we were actually trying the complete graph. Okay, maybe, yeah, okay. So we were trying the complete graph because, okay, we didn't have any motivation for doing something different. But what I was saying is that one can probably and possibly use and adjust those weights in such a way that, because at the end of the day, when you select those weights, you are making things easier in some directions and more difficult in some other directions. So we believe that if, for example, you wanted to propose not just morphisms that make the network more complex, but rather more simpler, again, if we don't do anything with the weights, these things will always tend to go towards where you have more stuff. I mean, where you're going to get better value of loss function. But then maybe by adjusting the weights, you could perhaps start exploring a little bit more often going backwards. And of course, like in this big optimization problem, going backwards could also be trying to go to escape local minima in a sense. Like you don't want to end up in very complex models, but then actually maybe the best answer was a complex model, but that came from a different branch. So of course you would like to go back a little bit and explore that. Yeah, but one thing that is important here to highlight as a general idea is that one of the reasons why we wanted this Wasserstein approach was because we wanted to talk about accelerated methods as well. And so in that framework, we had the geometric tools to propose that type of stuff. Of course, we could have said like, okay, let's just try to run some particle dynamics, similar to what I was doing here, without ever talking about the gradient, descent, and so on and so forth. But for us, we also wanted to see what would happen with this accelerated dynamics. And for that, we needed this framework, this geometric framework. So that's kind of important to highlight because, of course, you know, the similar concept could be applied for other particle dynamics, even if they are not necessarily related to a gradient structure.
Okay, there's a question from Leon. I'm going to unmute him.
Hi, Nicholas. Thanks for the interesting talk. I've got a question regarding this interpolation which appeared in this semi-discrete continuity equation. Yeah. I'm just wondering, is it an option to just mimic the product rule such that you have a product of two gradients plus the product of a Laplacian and a node function? And then you don't have, so if you just expand the divergence of gradient phi times mu, then you should have something which is defined on the same, so on the nodes and on the edges. Would that be an option somehow to avoid this interpolation?
So, okay, so I can tell you what is the perspective that I have on the interpolation equation. I'm not sure, you know, if you can actually do what you were saying. I'm not sure if you know, if one can make it work in that way. But I can tell you that, so for example, in the original paper of Jan Maas, you know, this choice here was very specific. It was the logarithmic interpolation. And the reason why he chose it that way was because he wanted to recover basically the result of Otto on the heat equation, that the gradient flow of the entropy with respect to this Wasserstein distance was or coincided with the heat equation on the graph. So the only way to make that happen would be to choose this theta to be logarithmic interpolation. In particular, the equation would become linear. So that would be one choice. But then, for example, when you have a potential, at least in this formulation that I have here, when you have a potential, then the logarithmic interpolation on the mass is not going to give you a linear equation. What you would need to interpolate is the mass times e to the potential, or e to the negative the potential. If you do that, then you recover again a linear equation, which is also another way of trying to do, instead of doing particle dynamics as I suggested, you could do something deterministic where you run those graph equations. It could be linear, in fact, like as I said, by choosing the interpolation appropriately. And then, okay, so this would give you a flow on measures and then on the graph. And then, of course, the idea would be to decide whether you want to, I mean, how would you extract from a distribution on the nodes a single node? Because this is like, okay, I talk about how you lift the problem, but then of course for us, we need to bring it down to say, okay, I need a concrete node to evaluate. I don't want to stay with measures all along.
Okay, yeah, thank you.
Okay, so let's move to the breakout rooms to continue the discussion. So thanks for the great talk, Nicholas.